Good day, everyone. The topic that we'll discuss of our group in elementary statistic and probability is the normal probability distribution. Before we start, I just want to remind you the mission and vision of our school, the Tanawan Institute. So let's start. The objectives of our topic are, after completing the topic, students should be able to determine the continuous random variable or continuous probability distribution. Determine the normal probability distribution. Solve the mean and variance of normal probability distribution. Determine the standard normal probability distribution. Solve the z-score and determine the value of z-score in the z-table. Describe the bell shape.
Continuous random variable or continuous probability distribution can take on an infinite number of possible values corresponding to every value in an interval. Continuous random variables are usually measurements. Examples: height, weight, the amount of sugar in an orange, and the time required to run a mile. For example, we might have a random variable that takes on any value between 5 and 6. So a random variable might take on the value 5.15, 5.5, or 5.54093 or what have you. Any of the infinite number of values in between 5 or 6 or common one on that we see. We have a random variable taking on any positive value, so any value between 0 and infinity. Example: distribution of height of students of BSE Math. Now height is continuous random variable and is going to have a continuous probability distribution. And it looks something like a smooth version of a histogram. A little loosely speaking, values of the variable where the curve is high are more likely to occur than where it is low. So here we would be more likely to get a height in this range than way out here in the extreme. We model a continuous random variable with a curve f of x is called a probability density function or PDF. A continuous random variable is now defined at specific values. Instead, it is defined over an interval value. However, you can calculate the probability of a range of values. It is very similar to z-scores and normal distribution calculations that we'll discuss later. Here is another example of continuous probability distribution. The distribution of time to failure 1,000 of hours for a type of light bulb. Values the random variable can take on are given here on the axis and the probability density function f of x. F of x is a function giving the height of the curve at those value of x. F of x represents the height of the curve at point x. An important notion is that for continuous random variables, probabilities are areas under the curve. Here's a continuous probability distribution for a random variable x. And the height of the curve is represented by f of x, and the probability the random variable x falls in between two values, a and b, is simply the area under the curve between a and b. One important notion here is that the probability the random variable x is exactly equal to any one specific value is 0. We could say that the probability the random x is equal to the value of a is 0 for any a. P times x is equals to a is equals to 0. We could think of point A here as infinitesimally small point with infinitesimally small area above it. We call the area 0. So the probability that x is equals to a for any a is 0. Let's say the probability that x is equals to 3.12, that's going to be equal to 0. P times x is equals to 3.12 is equals to 0. So from the practical point of view, it is only going to make sense to talk about the random variable x falling in an interval values. One implication of what we just talked about here is that this probability would be the same as saying the probability that the random x is greater than or equal to a less than or equal to b. We can switch less than or equal to a to with less than. It doesn't matter because the probability the random variable x is exactly equal to one specific value is 0. For any continuous probability distribution, f of x is greater than or equal to 0 for all x. This means that f of x has to be at least 0 everywhere. Note that there is no upper bound on it. It can take on values greater than 1. One restriction is that the area under the entire curve is equal to 1. And so, these two restrictions ensure that all probabilities lie between 1 and the probability of something happening is 1. Normal distribution is a probability distribution of continuous random variables. You can see in the picture that the data can be distributed or spread out in different ways. It can be spread out more on the left or more on the right, or it can be all jumbled up. But there are many cases where the data tends to be around a central value with no bias left or right, and it gets close to a normal distribution like this. A normal distribution is a bell-shaped frequency distribution curve. Most of the data values in a normal distribution tend to cluster around the mean and is often called a bell curve because it looks like a bell. Many things closely follow a normal distribution. The heights of the people, size of things produced by machines, errors in measurements, blood pressure, and marks on a test.
Here we see the four characteristics of a normal distribution. Normal distribution are symmetric, unimodal, and asymptotic. In the mean, median, and mode are all equal. A normal distribution is perfectly symmetrical around its center. That is, the right side of the center is a mirror image of the left side. This means that the distribution curve can be divided in the middle to produce two equal halves. The symmetric shape occurs when one half of the observation fall on each side of the curve. There is also only one mode, or peak, and a normal distribution. Normal distributions are continuous and have tails that are asymptotic, which means that they approach but never touch the x-axis. The center of a normal distribution is located at its peak, and 50% of the data lies above the mean while 50% lies below. The middle point of a normal distribution is the point with the maximum frequency, which means that it possesses the most observations of the variable. The midpoint is also the point where these three measures fall. The measure of the mean, median, and mode are all equal in a normal distribution. The probability density function of a normal random variable x is determined by two parameters. This is the expected value and the standard deviation of x. The normal probability density function is bell-shaped density curve that is symmetric about the value of the expected value. Its variability is measured by standard deviation. The larger the standard deviation is, the more variability there is in this curve. You can see in the picture the variability in the curve, the standard deviation rule and empirical rule. It tells us that for a normally distributed variable, the following are true. Approximately 68 of the data lie within one standard deviation of the mean. P, the expected value minus the standard deviation less than x less than the expected value plus the standard deviation. Approximately 95% of the data lie within two standard deviation of the mean. P, expected value minus the standard deviation is less than x less than expected value plus 2 the standard deviation. Approximately 99.7% of the data lie within three standard deviations of the mean. P, expected value minus 3 the standard deviation less than x less than expected value plus 3 standard deviation. This picture illustrates the location of every standard deviation rule. It is good to know the standard deviation because we can say that any value is likely to be within one standard deviation. 68 out of 100 should be very likely to be within two standard deviations. 95 out of 100 should be almost certainly within three standard deviations. 997 out of 1000 should be. We began to get a feel for normal distributions in the exploratory data analysis or EDA section when we introduced the standard deviation rule or the 68 minus 95 minus 99.7 rule for how values in a normally shaped sample data set behave relative to their sample mean or x bar and sample standard deviation or s. This is the same rule that dictates how the distribution a normal random variable behaves relative its mean. And standard deviation sigma. Now we use probability language and notation to describe the random variable's behavior. What is the mean and variance of a normal distribution? The parameter expected value is the mean or expectation of the distributions and also its median in mode. While the parameter of standard deviation, the, while the parameter of sigma is its standard deviation, the variance of the distribution is variance. A random variable with a Gaussian distribution is said to be anormally distributed and is called a normal deviate. Look the table. It shows a sample value of x and the probability, wherein the value of x are x sub 1, x sub 2, x sub 3 up to x sub n, and the probability are p sub 1, p sub 2, p sub 3 up to p sub n. The mean is also called as expected value, wherein the mean is equal to summation of every value of x and probability. The variance is equal to the summation of squared of every value of x minus the value of mean multiplied the value of probability. What is standard normal probability distribution? The standard normal distribution is a normal distribution with a mean of 0 and standard deviation of 1. The standard normal distribution is center of 0 and the degree to which a given measurement deviates from the mean is given by the standard deviation.
When using a standard normal distribution, we will use z to refer to a variable in the context of a standard normal distribution. A z-score is a numerical measurement that describes a value's relationship to the mean of a group of values. Z-score is a measure in terms of standard deviation from the mean. If a z-score is 0, it indicates that the data point score is identical to the mean score. A z-score of 1.0 would indicate a value that is one standard deviation from the mean. These scores may be positive or negative, with a negative value indicates the score is above the mean and a negative score indicates it's below the mean. These scores reveal the statistician and traders were a analysis to adapt scores from various data sets to make scores that can be compared to one another more accurately. Here is the z-score formula. In general, the standardized value z tells how many standard deviations below or above the mean the original value is and is calculated as follows. Z-score is equals to the value over mean divided by the standard deviations. The convention is denote a value of our normal random variable x with the letter small x. Now you can see the z table of a negative value where in the table entry where z is the area under the standard normal curve to the left of z. And then the z table of a positive value where in the table entry for z is the area under the standard normal curve to the left of z. This table can be downloaded in some site. Here is the standard normal distribution with percentage for every half of a standard deviation and cumulative percentage. As you can see in the graph, the location of the z-score, standard deviation, and the cumulative percent. And here is a graph of normal distribution is standardized or converted to the standard normal distribution. In standard distribution, you can see below the value of the data x, while the standard normal distribution, you can see below the z-score. Z-scores versus deviation. Z-scores versus standard deviation. Standard deviation is essentially a reflection of the amount of variability within a given data set. Standard deviation is calculated by first determining the difference between each data point and the mean. The differences are then squared, summed, and averaged. This produces the variance. The standard deviation is the square root of the variance. The z-score, by contrast, is the number of standard deviation a given data point lies from the mean. For data points that are below the mean, the z-score is negative. In most large data sets, 99% of values have a z-score between -3 and 3, meaning they lie within 3 standard deviation above and below the mean. So after we discuss the topic, here are some examples that will help you to understand the topic. Our example number 1, it involves the continuous random variable, the z-score, and the z-table that we use. Example number 1, young woman's height. A height of a young woman can be defined as a continuous random variable with a probability distribution, where the 64 is the mean and the 2.7 is the standard deviation. What is the probability that a randomly chosen young woman has height between 68 and 70 inches? Our probability of y is greater than or equal to 68 and less than or equal to 70. Here's the solution that we made. We use the z-score wherein the value minus the mean over the standard deviation. We first take the 68 minus 64 over 2.7. The z-score is equals to 1.48. And the next is the 70 minus 64 over 2.7. The z-score is 2.22. Wherein the z, or the probability of z is greater than or equal to 1.48 and less than or equal to 2.22. So we use the z-table wherein the value of 2.22 is equals to 0.9868 minus the value of 1.48, and z-table is 0.9306. So the value of our probability is 0.0562, wherein in percent, there is about a 5.6 chance of that a randomly chosen young woman has a height between 68 and 70 inches. Look this table where you can see the in between the 68 and 70. The height is in the inches, and this is the normal curve. You will see the normal curve. So, okay, we're next on the next sample in the normal probability distribution. Example, weights of newly born babies. In the table, you will see the measurement or the weights of the babies. Now we will need to find what is the frequency and relative frequency of a baby's weights that are within a 1 standard deviation from the mean, 2 standard deviation from the mean, and the 3 standard deviation from the mean. So this first we will first get the mean, wherein the mean is equals to the summation of the value of x over the number of value. So mean is equals to 220.09 over 36 is equals to 6.11. So our mean is 6.11. Then now we need to get the value of standard deviation. First we get the value of x minus the mean. So 2.24 minus 6.11 is equals to negative 3.87, and the first line of the table. And then we get the squared of x minus the mean. So it is equals to 14.9769. After we computing all of that value, we need the summation of the x minus the summation of the squared of x minus the mean for the formula for the standard deviation. So now our summation is 92.9409. So getting the value of standard deviation, square root of 92.9409 over 36. So our standard deviation is 1.60676 or 1.61. And now we create a normal curve using the mean 6.11 and the one standard deviation that we need to find. So the formula that we will use is here. The probability of x greater than the mean minus the standard deviation and less than the mean plus standard deviation. So 6.11 minus 1.61 is equals to 4.5. The standard deviation from the mean. And 6.11 plus 1.61 is equals to 7.22. So from the mean, one standard deviation from the mean is equals to 26 out of 36 baby's weight is or 72%. And now you can see the next table and the next graph. They create a normal curve using the mean 6.11 using two standard deviation. So the formula is the probability of x greater than mean minus 2 times the standard deviation and less than the mean plus 2 times the standard deviation. 6.11 minus 1.61 times 2 is equals to 2.89 and 6.11 plus 1.61 times 2 is equals to 9.33. So our two standard deviation from the mean is 95% or 34 out of 36. So now the third is the three standard deviation in the probability of x is equals to the mean minus the 3 times the standard deviation and, and the less than the mean plus 3 times standard deviation. So 6.11 minus 1.61 times 3 is equals to 1.28. And 6.11 plus 1.61 times 3 is equals to 10.94. So our 3 standard deviation from the mean is equals to 100% or 36 out of 36. So now, next to the example problem 2.1, within the normal probability distribution, a machine produces electrical components. 99.7% of the components have lengths between 1.176 cm and 1.224 cm. Assuming this data is normally distributed, what are the mean and the standard for deviation? Here, the mean is a halfway between the 1.176 cm and the 1.224 cm. So you can see in the graph here, the 1.2 is their mean. So 1.76 plus 1.224 cm divided by 2 is equals to 1.2 or 1.200 cm. This is our mean. And the 99.7% is the 3 standard deviation either side of the mean, a total of 6 standard deviation. So here, a 1 standard deviation is equals to the 1.24 cm minus 1.776 cm divided by 6. So it is equals to 0.048 cm squared over 6 is equals to 0.008 cm. And this is the result on the graph. You can see. So, 1.2. So, yung 0.008, we will subtract it from 1.2, our mean. So, we can see the value here, the 1.192 besides the mean, and the 1.208 from the right of the mean. So, our next problem, the example problem 2.2, normal probability distribution. The freshest tea company packed tea in a bags marked as 250 grams. A large number of packs of tea were weighed, and the standard deviation were calculated as 255 grams and 2.5 grams respectively. Assuming this data is normally distributed, what percentage of packs are underweight? So now, you can see the following diagram shows the 1, 2, 3 standard deviation on either side of the mean. So in this graph, you will see this. So 250 grams is 2 standard deviation. Below the mean, since 95% of facts are within 2 standard deviation of the mean, it follows that 5% divided by 2 is equals to 2.5% facts were underweight. So Lisa is a associate at a large auto dealership. She motivate herself by using probability estimate of her sales. For Sunny Tuesday in May, she estimates her car as follows. So you can see in the table. So the car sold is 0, 1, 2, 3, and the probability is 0 0.3, 0 0.4, 0 0.2, and 0 0.1. So let's find the mean and the variance of x. So here the graph. So the formula for the mean is equals to the summation of value of x and the times the value of probability. And the formula for the variance is the summation of squared of value of value of x minus mean times the value of probability. So here the sample computation, how to get the mean, the summation mean of, and the summation of variance. So the variance is, for the mean is 0. So 0 times 0.3 is equals to 0. So 1 times 0.4 equals to 0.4. 2 times 0.2 is equals to 0.4. 3 times 0.1 is equals to 3. And the summation of all these mean is equals to the 1, it is equals to 1.1. The variance is the formula for our variance is here. So 0.0 minus 1.1 squared times 0.3 is equals to 0.360, and so on up to the value of x of 3. So the variance is equal to 0.89. So the example for mean and variance normal probability distribution 3.1. The example is decoding a single unfair die for fun. Imagine a weight die. So we have these probabilities. 1, 2, hanggang 6. So 0.1, 0.1, 0.1, 0.1, up to 0.5. Then, here's the table. You can see the value of mean. So the summation of every value of x times the value of p. So 0.1, you can see on the table, 0.2, 0.3, 0.4, 0.5 plus 3. So, the expected value is 4.5. That is our mean. And the next is for the variance. So here, the summation of variance is dx. Oh, we first get the summation of the x squared times p equals 0 0.1, 0 0.1. And the variance is the summation of x squared p minus the mean squared is equals to 23.5 minus 4.5 squared is equals to 3.25. Our variance is 3.25. So our example number 4 for standard normal probability distribution is this score. So a survey of daily travel time had this result in a minute. So 26, 33, 65, 66, 28, 34, and so on up to 34. The mean. And now we're going to example problem number 4, the standard normal probability distribution and the z-score. So a survey of daily travel time had these results in minutes. So 26, 33, 65, 28, 34, 55, 25, 44, 50, 36, up to 34. So they are given the mean is 38.8 minutes and the standard deviation is 11.4. But we are going to solve the mean so you can see how to get it. So the summation of x over n, so 776 over 20 is equals to 38.8 minutes. So that is our mean. And then next, you can see the graph of how to solve the standard deviation. So getting the value of x minus the mean. So on the first line of the table is 26 minus 38.8 is equals to negative 12.8. So the squared of the value of x minus the mean is equals to 163.84. Then solve for the summation of all the squared of x minus the mean. So our standard deviation is the square root of 2,599.2 over 20. So our standard deviation is 11.40 or 11.4. So as you can see on the table, now we get the z-score. We using the z-score formula. So the z-score formula is the value minus the mean over the standard deviation. So the first on the line of the table is 26 minus 38.8 over 11.4. So his z-score is negative 1.1228. As you can see on the graph where it is located.